we're an interdisciplinary group of researchers from educational psychology, engineering, computer science, medicine, history. And so we're an eclectic group when we're all interested in studying learning and cognition and affect and how they co-occur and how we can look at that in the context of technology-rich environments. And we're dealing with a variety of different age groups, and we have lots of different research partners from the Simulation Center here at McGill to the Institute of Health Sciences in Hong Kong to Rocky View School District in Alberta. You know, we're all over the place, which is a lot of fun. And our goals are really to develop global communities of learners and teachers, to examine the role of affect, emotion, culture, decision-making, and communication, looking at three lenses: cognitively and socially guided learning, emotional engagement and disengagement, and the innovations of science of assessment that need to co-occur when you're developing these new signatures, looking at affect and cognition hand in hand. So briefly, there's 19 universities involved in this, 6 countries: Canada, US, Germany, Australia, Denmark, and Hong Kong. These are the disciplines that we have that I already talked about. And we have 5 interdisciplinary research centers, as well as 1 nonprofit computer research institute and 2 educational ministries. So all in all, we have 17 co-applicants, 1 collaborator, 12 partners, and 4 advisory board members. So with that little briefing on who we are, as I don't think I need to go too much into this since I just talked about it. Why are we doing this? Today's youth are ready to live, learn, and work in a knowledge-based digital age. They find technology engaging, and they use it to problem solve, inquire, and communicate in ways that reflect 21st century skills. However, in comparison, the use of technology in regular classrooms is somewhat stilted. In other words, we have all these wonderful bells and whistles we get to play with outside of school, and then our toys are taken away. And they're not just toys, they're actually digital tools for learning. And so our goal is to make it more realistic, to bring the fun stuff into the learning. This is our Atlas Lab. You'll see other lab members in the audience. And who's on first? Maida?
Yes.
Let me welcome Maida Kazemi. Kazemi Tabar.
A hard name. So some of you might be familiar with BioWorld from before, but we will go over it thoroughly and just show some of its features and environment, and for the others which haven't seen it from before. So it is a technology-rich environment based on theory, which situates learning in meaningful case-based activities and provides opportunities for students to practice investigating medical patient complaints and diagnosing their different hypotheses, and receiving also expert feedback. Several cognitive tools are incorporated to support this clinical reasoning. Some of them are the evidence table, the belief meter, and the consult tool. So in these slides, I will take you over through some main spaces of BioWorld. This is the first one. There are problem, chart, library, and consult spaces, which I will show you here. Every problem which we face in BioWorld starts with a patient case history. So, for example, in this part, it says things like, yesterday Raymond had to call in sick for work due to upset stomach and intense fatigue. And so it will go over the patient history, and the participants are encouraged to highlight parts of information which they think are important, and they can add them to their evidence table, which is a kind of a virtual notepad which they can use throughout this problem-solving activity. They also have a managed hypothesis, which they can choose one or more main hypothesis and choose one of them as their main hypothesis, and they can use this belief meter to rate their confidence level to see whether, to show whether they are confident or not, from 0 to 100%. And so this is how the belief meter and managed hypothesis look like. And in the next space, we have the chart, which is a drop-down menu of a large number of tests which they can use, and the results will automatically be added to their evidence table. There's also a part for vital signs, and students can use this space to order as many tests as they think are necessary. In the next space, we have the library, which they can use to information. These information are like related to diseases, the diagnostic tests, and the medical terms. If they find parts which they think are important, they can highlight them and add them to their evidence table also. And they can use it and save it here. The next part is the consult space, where students, whenever they are stuck in the problem-solving activity, they can use to receive hints and prompts. If they are, this consult is contextualized. So, for example, if they are in the problem space, and if they press consult, they will receive hints on which evidences might be important to highlight. If they are in the chart and they press consult, they will receive hints on which tests they might want to order. And if they are in the library, they might receive hints on which information they might want to read. For example, if the person who was using the consult here was in the library and received this hint, who might want to read about hyperthyroidism. So in summary, BioWorld provides tools for cognitive reasoning skills, and some of these are cognitive apprenticeships with virtual cases and charts, evidence collection, supported and stored dynamically for continual review, support for multiple differential diagnosis, ability to order diagnostic tests to confirm or disconfirm hypotheses, online library resources, and expert pattern solution. There are also other spaces in BioWorld like evidence categorization and argumentation, but in interest of time, we'll just show them in the demo, which Eric will show, and he will also explain about the methodology and how we will use how metacognition is supported in BioWorld.
The format, the table is So basically, the rationale for our research is that we're interested in examining the cognitive and metacognitive activities that occur while learning with BioWorld, because we basically hypothesized that the cognitive tools that Maiden just talked about support the kind of like building blocks for those metacognitive activities. So in studying these metacognitive activities, we've relied on the model that was proposed by Meyer and Al in 2006. So I actually brought you in kind of like our coding scheme with an actual example. So what I'd like to do next is to kind of like just show an example of a student performing what we call the think-aloud protocol. So we use think-aloud protocols to get information on what they're thinking about and what they're attending to while they use BioWorld. So basically they just think aloud while they're trying to solve the case. So what I'll do is I'll just show you the video, and then in the meantime I'll distribute the actual coding scheme with the example of the transcript that we coded. And we'll just refer to it back and forth while we're going through the presentation. So let's see if this click.
Maybe a cortisol. I'm still thinking of hyperthyroidism, but I think that because the pheochromocytoma would be way more dangerous for her, I was trying to figure out a way to rule it out, even if I don't think it's the main thing. Because there's a small chance that it could be, and we need to make sure that's not what's happening. Because the symptoms would also kind of go with that. I guess the symptoms is normal, I'm not sure. Normal result. From what I understand, this looks normal. Is there some test I would order to see if it's the anxiety? That's more of a psych. It's not a lab thing, it's a psych exam. Oh, a physical exam for sure. But this is something I would just always think of. Skin exam, I think it's too specific. but I would look at her skin to see if she has a very dry or skin or something is happening, and I would look at the eyes to see if she has an exophthalmos, but I don't think that's the same as an eye exam. Tox screen. That's a good one. I didn't even think of that. That can be.
Okay, so I think that's enough examples. So basically afterwards, when we look at those recordings, we basically transcribe everything that the student did, and then using our coding scheme with the categories and the subcategories, we actually match the codes back to what they said, to kind of like interpret and get a better ideas of the activities that they engage in.
Can I ask questions while you present?
Yeah, sure.
When you're transcribing, do you write down what you were doing when you were saying something, like without using the screen recording, like saying she showed this and then said this? Do you mark them
Right,
with written transcriptions, or you just?
We do record the behavior. Some of the behaviors get stored, of course, in the log file.
Yeah.
So, for example, when they switch screens, we try to limit our inferences in regards to the behaviors by just noting where they actually point, like with their clickers and stuff, because we don't want to make inferences on what they're attending to, because we don't have like eye trackers and stuff.
No,
that's actually session 2 with you.
So to answer your question.
But we have done like the combination in one study, Genevieve, when she was looking at the experts, did the three, like we have the Camtasia and the log files and think aloud side by side. But here, I don't think you have the log, well, you have the log file data, but I don't know if you're looking at that specifically or just what they're doing in the context of Camtasia.
Yeah, basically in your transcripts, all the log file entries are marked as LFE, and then the think aloud protocols are marked as TA at the beginning of each line, so we can still push and keep track.
Oh yeah, there's one of them.
Have you analyzed any of this yet?
Well, this was part of a previous study that we looked at how they kind of like use the console tool while using Bio and stuff. Like we'll come back to that like later on in the presentation.
Well, you're
and stuff.
actually talking
Explain
about
the
data
context.
analysis or not? I forget.
I'm sorry?
We
We
don't
can present some of the data
Yeah.
in the next few slides.
Yeah.
So I saw what you're referring to. I got no response. Thanks.
So basically now we're going to talk about how we developed our coding scheme and what we mean when we're saying that we're defining metacognitive processes in the context of BioWorld. So revisiting the article, the Meyer 2006, there were definitions that were created from this research, and if you want to know a little bit more about how it was adapted to the medical context, you can look at Lajoie from 2009. But basically what happened was there were 6 subordinate categories that were made, and they're orientation, planning, executing, monitoring, elaborating, and evaluating. And basically what these are the what, when, how, and why of these metacognitive processes in the area of medicine, what we're talking about, medical diagnostic procedures and problem solving. So we used 2 levels of analysis. One of them was the macro level and the other was the micro level. These were a deeper definition and more specific definitions of the macro levels. So as Christina said, we used some of these as the macro, and also we had no code and uncodable for parts where we couldn't code and for parts where we needed more codes to match. And we had, Christina will speak about the valence of some of these codes.
So now we're just going to show you actually how we define and identify these metacognitive activities through the BioWorld interface. So as Eric mentioned, we have think aloud protocols and we have log files, and all of these sort of show up in different areas of the BioWorld interface. So we'll go through these 6 categories of the metacognitive processes that we use for our coding scheme. So first we start with orientation, which is just that the student is orienting themselves to the problem. So we see them looking here, if you look at where it's highlighted, they'll be looking at the patient problem. So they'll find out what's wrong with the patient. And then from there, that's where they start hypothesizing. So they start thinking what could possibly be wrong with this patient, and they can look at the evidence tablet and they can identify or repeat important information that will be pertinent for them to make the actual diagnosis. And also in this stage, they activate their prior knowledge. If they're thinking it's diabetes and they already know something about diabetes, they can state here that, oh, I know a little bit about this, so this is where I'm going. Then if we move on to the planning phase, they're in this phase where they're actually going to form an action plan. Again, they can look at the problem. Here they can look for particular information, so they can go to the library with a plan and say, I need to look this up, so we can see them actually on the log file and when they state, in this area I'm going to look up diabetes because I need some more information on it. So they have a clear sub-goal, it's an action plan that they're going to do. And they can also use external sources of information, so that would be hitting the console button to get external information. It would be like asking a doctor for some help in problem solving. And then also they can organize their class by sub-questioning. So they have a working hypothesis and then they say to themselves, well, I know it's, hypothyroidism, so what do I need to do next? Oh yeah, I need to order this test. So we get some of that information in the Think Aloud. And then the executing is basically actually executing the action plan. So I said I was going to order a chest x-ray, and then you see in my log file I ordered the x-ray. So we code that as executing because they're carrying out the actual plan that they had. And then in monitoring, this is where the student actually starts showing that they're making links and they're claiming understanding, or it's a part where we see that they're noticing inconsistencies. So they had a working diagnosis, and maybe by running all these tests, they said, oh, I found the information I need, so this increases my understanding of what's going on. Or what they were thinking doesn't match at all with what the data is that they actually obtained from their tests. So therefore, they're noticing an inconsistency, they're a bit confused, and then they start checking the plausibility of the actual working hypothesis that they have. Evaluation, they again can look at the evidence table and they start checking all of the data. They go back to the problem, might reread the problem and see, is the evidence that I have consistent with the problem and the diagnosis that I'm working with. They then can go and manage their hypothesis, so they can increase the probability by justifying or decrease the probability. So justify for one and decrease probability for the others. They can do it that way. The valences, we coded basically if they increase the probability of a diagnosis that was false, that would be negative because they're not going in the right direction with this, but they're still increasing their probability. And the same thing with justifying. The positive valence means that they're actually working towards a correct diagnosis and they realize that this is more probable. And in the event that a student is a little bit unsure of which diagnosis they're actually finding, sometimes you see here, I don't know if you can see, but it says new and current both at 50%. So the student here is not really sure which way to go with it, so they kind of decide that they're just going to submit it anyway without actually justifying more or less which diagnosis it is. In the elaboration phase, they do the same thing where they conclude, yes or no, I'm going to submit this potential diagnosis, but here you see that they elaborate a little bit more on why they're actually going to submit the diagnosis. So they can use the library to connect the lab test and connect parts of the tests from the library to show that it's actually relevant to their current diagnosis. And the valence is the same as it was in the previous slide. So either they confirm it by using the right information, or maybe they're going with a working diagnosis, but the information they have is irrelevant, so we wouldn't code that as negative. And then finally, they submit their current hypothesis. Only this way, they actually justified why they did it. They didn't just simply give up.
So we have provided some examples so that you can see here. These are some segments which we have derived from the many transcriptions which we have. For example, in one part the student says, this is a Think Aloud. Let's do the one that I didn't do, the random. So we have coded this under formulating an action plan with a category or a micro level of planning. And in the next phase, the student adds a test, random blood glucose level, which has a result of normal, and we see that this is a log file entry. So we have coded it under executing action plan. And another example would be a Think Aloud of normal. So we see here that the result was normal. So it seems that the required information hasn't been found. So we have coded it under with a negative valence, with a macro level of monitoring. And so in the next part, the participant has a formulating an action plan, as Christina said, that the person is trying to formulate a plan. And the participants switches area from chart to history screen, so this is a log file entry, and we have coded it under executing action plan. And another example would be, she feels dizzy. That's why I was thinking hypoglycemia. So these two sentences don't seem to be relevant, so we have coded it under connecting parts of text by reasoning, but with a negative variance, with a macro level of collaboration. So I'll now hand it over to Eric and Tara.
So Eric and I are going to talk about an overview of the methods we used in our research to talk about how metacognitive and cognitive activities are happening during diagnostic reasoning. So the first thing we're going to look at is the combination of these measures that were used to capture both the, the processes and outcomes in these diagnoses, as well as how we sampled, segmented, and coded the data. And then we're also going to talk about issues that are going to come up with the theoretical, methodological, and instructional assumptions we made in this approach. And finally, we're going to wrap up with a discussion about where we want to take evaluating BioWorld in the future.
Great, so I won't have to walk over there. So basically in the methods that we use to evaluate BioWorld, we make a distinction between online and offline measures, which was actually a distinction that was done by, which was described in a special issue that was co-edited by Jeffrey Green and Lajoie, an educational psychologist, in 2010, so a very good reference. By the online measures, so I'll talk a bit about the online measures first, and then Tara will elaborate on the offline one. So what we mean by online measures are measures that are basically administered or that target the processes that are involved during task performance. And these processes, we assume, mediate the actual outcomes. So some of the online measures that we've used, we've alluded to already. So we rely on think-aloud protocols to basically get information on what they're thinking about, what they're attending to while using BioWorld. We rely on log file entries, which are computer records of all the behaviors that they engaged in while using the software. And as a complement to this, we also use Camtasia, which is how we got the recording of what they do while using software, so every little things that they click on, and we also get their faces. So basically, there's different aspects of these cognitive and metacognitive activities that we're interested in while we analyze our data. So here you can see an example of the software that we use to code. So, and we also rely, of course, on a much more simpler approach with the example using the Word document here. So basically, we're interested in terms of what are the frequencies of these activities. Do they engage in certain activities more than others? We're also interested in the sequence in which they occur, and whether or not there's discrete phases throughout the diagnostic processes where these activities tend to cluster around more, or whether or not they're linked to certain features, for example, in BioWorld. So in the next slides, I'll talk about a bit about some of the evidence that we found for converging these different data sources.
So yeah, we also used offline measures, or measures that occurred after a task was performed, to assess the impact of the cognitive and metacognitive activities. Some of the measurements that we used were novice expert comparisons that happen in BioWorld, as well as retrospective think-alouds done by expert physicians. And there are three main variables in our outcomes of the diagnostic process. We have efficacy, efficiency, and the affective. And the variables are recognized by these various indicators. So diagnostic accuracy, or the correctness of a final diagnosis, is an indicator of efficacy. Another example would be confidence, which is an indicator of affect. And that would be something as simple as someone rating how confident they were in their final diagnosis.
So in regards basically to our approach, there's 3 steps involved. So we first of all sample our data, and then we segment it and we code it. So in sampling the data, this actually refers to, and if you could go back to the next slide. Yeah. One right before. I planned this like going back and forth. So So if you can kind of like visualize the data as like all the activities that occur throughout this timeline. So in sampling the data, we're actually interested in just selecting parts of the data to bound our inferences to. So for example, in our past study, We've looked at the behaviors that occurred before and after they used the consult tool, so where they asked the physician for help. And so we sampled that data to basically make inferences about the effectiveness of that particular feature in BioWorld. So there's a couple of things that are noteworthy here. So in our past research, we found, first of all, evidence in favor of using these different data sources. So we found that the cognitive activities that occurred during the executing phase we found much more information in regards to log file entries. And we found that our inferences are much more reliable when we came for coding for the metacognitive activities that occur in the monitoring and the planning phases. So we found that we relied a lot more on the Finkel-out protocol. So actually using these different data sources, we're able to get a better picture of some of the processes that occur while they're diagnosing different diseases. Another interesting thing was that in coding for the goals, we actually found that we could increase the reliability of our inferences by considering the entire context, so the entire learning session, as opposed to all the other codes in your coding scheme, where we found that we were actually able to just base our inferences on using the data that was just sampled here. And some of the techniques that we use to try to determine whether or not a particular tool is effective, so we draw novice-expert comparisons, so looking between the novices and the experts to see whether or not they use certain strategies appropriately or inappropriately. And then we triangulate the data in regards to the processes with these different outcomes that Tara just talked about to get basically another idea in terms of like, well, did they actually find the right diagnosis, or were they really confident in a hypothesis that wasn't actually the right diagnosis?
So mentioned earlier, we have some issues we'd like to discuss with you about this project. Theoretically, how should we build on this model to account for the developmental aspects of metacognitive skills during diagnostic reasoning? And what other components should be added to better account for the novice-expert differences? Instructionally, how can the model inform the design of optimal tools embedded in the learning environment? And methodologically, how can we assess novice-expert differences and metacognitive skills based on this model?
And for future directions, we'd really like to kind of like extend the current model on the one hand to define like more of these metacognitive processes and how these different variables interrelate, but also to incorporate affect. So another area that we assume that the students are actually regulating their learning while they're learning with BioWorld is how do they actually feel when, for instance, they're trying to solve the case and then they're facing an impasse, so they're not really sure